On this week, we learned about how PN junction diode looks like and how it's made, and I explained with the mathematics and physics. Okay, there is a PN diode is a simple junction, two types of semiconductor, which is N type and P types. So here you can say like shaped like this. They are bounded here. They From the left side there is N type and right side there is P type. Okay, if we draw some energy levels, so as by constant of a varying level, there is no difference between those N type and P types. So we can know that this semiconductor is a totally neutral or a thermally equilibrium. So there is a differences between a conduction levels and balance levels. It's because of on the N types there is a majority carriers electrons, and on the P side as there is a holes are majority carriers. So if we draw a graph about a charges between those areas, we call it a depletion area. On the outside of depletion areas, they are electrically neutrals, and on the depletion area there is a less mobile carriers between them. So if we draw this a graph, we can, on the P side there is a negative charge, is space charge is here. We call it space charge because on this charge they can't be moved, so called as, which means they cannot move. They cannot work as a mobile carriers. So there is a negative charge and there is a positive charge. Okay, if we calculate those total charge of here on P side and N side, it should be same. So the integrations between those two, and P side charge and N side charge, should be equals. So what if we integrate all of those on the electromagnetics? If we, by Poisson's equations, if we integrate a charge, there is a electric field, not the electrical flux. Okay, then we have a electric field, so we can know that there is a electric field and electric potentials between a depletion area. So by here there is a depletion areas, there is some voltage potentials differences. So if we to calculate those bias, we can bring out some formally knowledge, which is bias voltages bias voltages are dependent on those matters. So like how much they heavily doped, or how many they have a carriers, or with how gaps are. Okay, from the quasi-Fermi levels, we know that if conduction bands and Fermi's level on differences between a Fermi level and conduction levels are major factors of a how much they have a mobile carriers and drift current and so on. And for the N types, for the P types, how much closely gaps are on valence band and Fermi level. And if we use those mathematical techniques, we can know those differences are the same as a intrinsic Fermi level and other doped Fermi levels, those differences. So if we bias those two sides which positively bias, the energy states becomes a rounded. Those bias gaps are shortened, and if we reversely bias, which means a positive bias on negative side and negative bias on the positive side, the gaps bias voltages gets higher. So using those phenomena, and that's it for this week.